Okay, I guess today is going to be our last class because we are almost there. So if you recall, yesterday we did your Stokes theorem. We did Stokes theorem, and what was that? That provided us with a relationship between a line integral and a surface integral. Line integral and a surface integral. Okay, so this one you may write under vectorial surface notation as this that we have already discussed yesterday. Okay, so now again, I mean, whenever you are given a problem, where you have to make use of Stokes theorem, the thing you have to look at is, I mean, whether from the input that is being provided to you, with the help of that, the left hand side is going to be simpler or the right hand side is going to be simpler. So depending upon that, you are going to evaluate it. Sometimes it may so happen that, like say, when you are told to evaluate a definite integral, like you can see there in the blackboard, I still haven't explained what the problem is, right? So it may be so, even without, employing the Stokes theorem, you can evaluate the integral in a much straightforward way. Okay, so that you have to look at. So now simply look at this problem. So the problem is about evaluating. This integral, where that vector field f is given by this, and where your s, it is nothing but this surface, which is the part of the sphere, your x squared plus y squared plus z squared equal to 4, that lies inside the cylinder x squared plus y squared equal to 1, and above the xy plane. Okay, so firstly, let us have a look at what the surface S is going to look like. What the surface S is going to look like. So obviously, you know that S, we have given the information that it lies above xy plane. So whenever we are going to consider the sphere of radius 2, what I am going to do, I am always going to consider it in the upper hemisphere. So it is going to be something like this. It is going to be something like this. So this is the sphere, your x squared plus y squared plus z squared equal to 4. And then what we have to do, we have to consider the cylinder given by x squared plus y squared equal to 1. So basically, it is going to be something like this. Something like this. Okay. So what we have to do, we have to consider this as our surface. We have to consider this as our surface. Is it okay? Fine. So now you can see that, I mean, if I would like to evaluate the curve of the vector function, it is going to be cumbersome, right? So it makes sense that perhaps converting it into a line integral is going to, reduce my effort. So now you know that from Stokes theorem, so this is simply equal to your C f dot dr, right? Where C is a positively oriented curve that bounds the surface S, right? So now what we have to do, we have to find out this curve C. So now, I mean, if I want to find out the intersection of this sphere and this what cylinder, this cylinder, that's nothing but a circular cylinder. So then, if you substitute this here, what you are going to get? You are going to get j square equal to 3. Is it okay?
Yeah.
Fine, j square equal to 3. That means j equal to square root 3 because I have been given that I am going to consider only the portion which lies above xy plane. So because j is greater than 0, so I am going to stick to j equal to square root 3. So this curve C is nothing but this circle x squared plus y squared equal to 1 and j is square root 3. Okay? So now what we want? What we want? I want the parameterization of this circle. Parameterization of this circle. So then you know that the parameterization is pretty straightforward. So this circle is given by simply cos t sin t, isn't it? So x is cos t, y is sin t because its radius is 1 sin t, and j is constant. It is this. Is it okay? And of course, your t lies between 0 and 2 pi. T lies between 0 and 2 pi. Okay. So now that means if I want to find out this double integral, that means this surface integral. Okay, so if I use your Stokes theorem, this is going to reduce to this. Okay, and then you know that this is nothing but a to b, and then what you do? It is simply eventually your f as a function of t, right? And then dot r prime t dt, right? So here a is 0, b is 2 pi, fine? And so this is going to become 0 to 2 pi. And let us write down what is f in terms of that parameterization. So it is xj. So that is, yeah, 3 cos t
plus root 3 sin t.
Root 3 sin t and sin t cos t, right? Cos t sin t. Okay, and then if I want to find out r prime t, that is simply minus sin t cos t 0, right? Sin t cos t 0. So this is eventually going to give you this minus square root 3 sin t cos t minus again square root 3, like this thing, dt. And you can see that cos t is the derivative of sin t. So once you integrate,
why there is a minus again?
Just a minute. Minus of, oh no. This is going to be plus. This is going to be plus. Okay. So anyway, this is giving you 0, straightforward. Yeah. Fine.
Yeah.
So even had it not been 0, so suppose it would have been something else because you had sin t, right? This derivative is already there. So this would have given you some powers of sin t, right? And for the limit 0 and 2 pi, that would have given you simply 0. So in fact, this result has some significance. So what we are going to do, we are going to consider some problems in our tutorial sheet. Yesterday, I had already given you some hint. I mean, whenever you consider a surface. Now, in order to find out the curve which bounds the surface, what you are going to take. So that becomes very, very important. Okay. So this one, in fact, even without evaluating all this stuff, I mean, by choosing the curve C in such a way that even without evaluating all this stuff, you would have been able to reach the conclusion that the value of the integral is going to be 0. So I think we have given a couple of problems in our tutorial sheet on that effect. So those are going to be discussed in our tutorial classes. Fine. So now, what we are going to do, we are going to go to, your divergence theorem. We are going to go to divergence theorem, and you should remember that this divergence theorem is due to Gauss. It is also called Gauss's divergence theorem. Okay, so now, so before going into that theorem, let us come back to if you recall, vector form of Green's theorem. And of course, you may recall that Green's theorem, it was considered on a planar region. It was considered on a planar region, right? And then we had found out that your what? Did we take something like this? Yeah, probably you recall. We got something like this, right? Because what happened there? I mean, in Green's theorem, it gave you a relationship between your a line integral and what? A surface integral, right? And in fact, this all happened in a 2D plan. Okay. So it makes sense that if you convert it into a 3D space, what it is going to become. So this line integral is going to be a double integral, that is surface integral, right? And the surface integral is going to be some kind of triple integral. I mean, this is just an intuition, right? So this should give you something like your Fn. So see, this was integral with respect to arc length. So now it is going to become surface integral, and this should become some triple integral over some reason this. So divergence of F, and instead of dA, it should become dV. Is it okay? See, this is still I'm talking about intuition only. And it so happens that our intuition is true. In fact, whatever I have written here, this one, that is nothing but the Gauss's divergence theorem. Okay, so just let me show you exact statement of Gauss's divergence theorem. So this is what it is. So here, as I have told you, that we are going to consider a 3D region. So that 3D region is E. So E is a simple solid region. So that means E at the same time can be considered as a type 1, type 2, and type 3 region in 3D. Okay? And let S be the boundary surface of E given with positive outward orientation. So you already know about this orientation. Okay, so whenever we are going to take some normal over the surface, it is going to be outward normal that we are going to consider. Okay, fine. So now what happens if F is a vector field whose component functions have continuous partial derivatives on an open region that contains E. So then what happens? This surface integral becomes this volume integral. Is it okay? So this is what it is. So now I would like to give you a quick outline of how you are going to prove it. How you are going to prove it. So remember the thing that we have assumed that E is a simple solid region. Okay. So even if E is not a simple solid region, but we would definitely be able to express E as the union of some simple solid regions. So then breaking the integral, so we can easily easily prove the Gauss Divergence theorem. So now I'm going to prove the Gauss Divergence theorem when your E is a simple solid region. That's it. Okay. So here what we have assumed, if you look at the figure here, what is being assumed, that we are assuming that here the way the figure is drawn, it looks like it is a type 1 region, isn't it? It is a type 1 region. Okay, so I'll come back to that. So I will draw the figure later. I will draw the figure later on. So this is my Gauss Divergence theorem. This is my Gauss Divergence theorem. So if I have to prove it, for a simple region. So now if you assume that your F is given by PQR, where the components PQR, they are functions of x, y, z, and they have continuous partial derivatives. Okay, they possess. So then what is going to happen? This one, your left hand side is going to be your S. Then your I can break it as I can break the left hand side as this, isn't it? Right? And the right hand side can be broken into your Is it okay? Fine?
Yeah.
Right? Right hand side can be broken into that. So that means if I can prove that this part is equal to simply triple integral of del P del X over E. This part is equal to this, and this part is equal to this. My job will be done. Is it okay? Fine. So what I'm going to do, I'm going to prove the third part. I'm going to prove that this is equal to this. So basically, and once I prove that, the other two parts you can easily prove. So what I'm going to do, I'm going to prove that your S, your R, K, sorry, this is not equal, and cap ds. So this is equal to triple integral T, your del R del Z dV, del R del Z dV. So that's what we are going to do. I'm going to prove this. Okay. So now I can come back to that figure. So since your E is a simple reason, so that is why it can be expressed both as a type 1, type 2, and type 3 reason. So in order to prove this part, what I am going to do, I am going to consider your E, that is capital E, that reason E, as a type 1 reason. So that means what I am going to do, So E is going to be equal to something like your XYZ belonging to R3, your such that your XY belongs to some domain D belonging to R2, right? And your J lies between some surface, your U1 XY and U2 XY. You already know this, right? Okay, so let us try to draw this. Suppose this is D. Suppose this is D, and then suppose your this is your region. This is your region. So the green one, this is the region E. This is the region E, which is bounded by this surface. This surface is J equal to U1 XY, and this surface is J equal to U2 XY. So is the figure clear? What I'm trying to say?
Yeah.
Fine? Okay. So now let us concentrate on the right hand side here. Let us concentrate on the right hand side here. So here this right hand side equal to this one. I can Taylor lifted your dv. Okay, so since I have considered E to be a type 1 region, so that is why this I can write it as this as D, and then for this I can write it as your what J equal to U1 XY to U2 XY, and then Taylor delta dz, and then simply dA. Is it okay?
Yeah.
Fine. So that means this is simply going to be your D, and once you integrate it, this is simply going to give you R, isn't it? And R between XY, this is the upper limit, and XY, U1 XY, this is the lower limit. Is it okay? Fine?
Yeah.
That is my right hand side. So now let me concentrate on the left hand side. Okay, fine. See, left hand side is this. Okay. Now if you look at this region E, it is bounded by see this surface S1, which is given by J equal to U1 XY, surface S2, which is given by J equal to U2 XY, and this surface and this surface. So the situation is the situation is something like this. The situation is something like this. You have an upper surface, you have a lower surface, and you have this surface. Is it okay? You have this surface. So this one was your U2 XY, this one was your U1 XY. Is it okay? So I was calling the lower surface as S1, this as S2, and I'm going to call this surface as S3. Okay, fine. So say suppose this is S3. Okay, fine. So this one I can break it into S1 RK n cap ds plus S2 RK n cap ds plus your S3 RK dot NF ds. Okay, so I'll move to S1, S2 later on. Let me just think about this S3. Okay, so now look here. Which one I was taking? Okay, anyway. This is my S3. So now, if you take, this is my S3. So if you take any normal to this surface, any outer normal to this surface, it is always going to be horizontal, isn't it? Yes?
Yeah.
It is always going to be horizontal, right?
Yeah.
And you know that my vector k cap, it is in the vertical direction, right? So that n cap here, if I take the dot product of this n cap, which is nothing but the red pencil, right? And k or negative k, whatsoever, what is going to happen? What is going to happen? The dot product is always going to be 0. Is it okay?
Yeah.
Fine. So
Yes.
just a minute. Let me just keep it in. Yeah. So that is why the third integral, it is going to vanish. Is it okay?
Yes. Yes.
Fine. So this is going to be 0. This is going to be 0. Now let us concentrate. Let us concentrate on the first integral. So once I can evaluate the first integral, then evaluating the second is very straightforward. So now let us look at this. So maybe what I'm going to do, I'm going to consider S2 first, so then S1 will be easy for me. Okay. Now here the outward normal is going to be something like this, n cap. Okay. So now you know that I mean whenever I want to evaluate something like this, where S is the surface, which is nothing but the graph of a function. So this simply becomes what? This simply becomes your f dot, and then if that surface is given by z equal to say, okay, so this is simply going to become, say, z equal to g of xy. This is simply going to become what? Minus p gx minus q gy
Plus R.
plus r dA. Is it okay?
Yeah.
Fine.
Yes. Yes.
So now you see what is happening out here. For this function, the first two components are 0, isn't it? For this function,
Yeah.
right? So it is simply going to give me. What? It is simply going to give me this RDA.
Yes.
And remember, this RDA, it has come because here this n cap, it is simply minus del u to del x minus del u to del y, comma, not necessarily n cap, like say a normal vector, because it would have been divided by its magnitude, and that would have cancelled with the other one. That would have got cancelled with the other one. Okay, fine. So basically, what I want to tell you, because this is an outward normal, it is on the top surface. The third component is always going to be equal to 1. So that is why it has become RDA. Is it okay? Fine. So that is why this part is going to give you simply this is going to become your D, and D, then R xy u2xy dA. Okay? So now let us look at this part. Because third part is already gone. So third part was there, but eventually this is the case. So now in the third part, what was happening? I mean this first part, what was happening? You will see that S1 is this surface, isn't it? The lower surface. Now, what is going to happen? If you consider a normal, it is going to be like in this direction. Is it okay?
Yeah, negative.
Right? So that means this is going to be simply this, and this, whatever may be. It is going to be, this third component is going to be negative one. Is it okay? Fine. So
Yes.
that is why this is simply going to ultimately give you minus r this, and this r here, r is a function of x, y, z, and z is u1 xy. Is it clear?
Yeah, now it is clear.
Yeah. So now you know that this is nothing but simply whatever we have got from the right hand side. Is it okay? Right? So similarly, the other two parts. I mean, because if you recall, I mean, when I broke that, theorem, broke that inequality, it has three components, each on the left hand side and the right hand side. So I have simply dealt with the third component. Now, second and first component, you will be able to deal with simply by considering your what?
E as a type 2 or type 3?
E as a type 2 and type 1. That's it. Is it okay? Now, at least you have got a glimpse, you have got an outline how to do it. Okay, fine. So then, I mean, please try to do the other two parts also at home. Although it is going to be more of a, it is going to be similar to whatever I have done. So now let us try to work out one example. Example. I'll just show it to you. So now, if you want to find out the flux of the vector field, over the unit sphere, So here, what you are going to do? See, here f is given by this. F is given by this. Okay. So just a minute. I'll just let me just write down f and then say y x. Okay. So you are told to find out the flux of this vector field over this sphere x squared plus y squared plus z squared equal to 1. So this is a beautiful example. See what is happening out here. Basically, you are to find what is flux. Flux is nothing but what? Your f dot ds, isn't it?
Yeah.
It is nothing but this. Okay. So if you use now divergence theorem, so this is simply going to become E divergence of f dv, right?
Yeah.
Okay. So now if f is this, divergence of f is going to be what? Del del x of z, del del y of y, del del z of x, isn't it?
Yeah.
So this is simply going to be 1 dv, right?
Volume E.
This is simply volume of E, and the sphere volume of E is 4 by 3 pi r squared. So simply That's it. Fine. See, such a like say complicated integral, you can evaluate it very simply by making use of your Gauss Divergence. Okay. So now let us consider another example. Let us consider this one. Again, you have to find out this. This is the A class, where S is the surface of the region E bounded by the parabolic cylinder Z equal to 1 minus x squared. Just let me write it down. Z equal to 1 minus x squared, that is parabolic cylinder, and the planes Z equal to 0, y equal to 0, and your y plus Z equal to 2, and your f is given by your xy y squared plus e to the power xz squared and sine xy. Okay, fine. So basically, you have to find out, and again, you know that I'm going to use divergence theorem. But before that, let me try to draw the figure. Okay, see, it is obviously bounded by z equal to 0 and y equal to 0. So this is x, y, this is z. So z equal to 0 is this xy plane, okay, and y equal to 0, that is xz plane, xz, right? Is it okay? Fine.
Yeah.
So basically, it is going to be in the first, and if I call this as the other octane, first and the second octane, if this is the second octane. Okay. So then z equal to 1 minus x squared. Z equal to 1 minus x squared. This one, it is nothing but this. Say if this is minus 1. This point is minus 1, this point is plus 1. Okay, fine. And then y plus z equal to 2. So this y plus z equal to 2, this in xy plane, what does it become? Simply y equal to 2. Isn't it?
Yeah.
Y equal to 2. So y equal to 2, it is going to be something like this straight line. And then again, I have, so this is going to come over here, this is going to come over here, and then here I am going to have this plane y plus z equal to 2, and that plane is simply going to be given by z equal to 2 minus 1. So basically, I am going to get something like this. Something like this. I'm going to get something like this. Okay. I'm going to get something like this. So this plane is your z equal to 2 minus y, and this one, it is your z equal to 1 minus x squared. And this line, this is y equal to 2. This line is y equal to 2. Okay. So now, what can you tell me? Which type of reason would be better to express this as? If I take projection on xz plane, I guess it is going to be better. That means what you have to do. Like say, if you take E to be equal to xyz belonging to R3 such that, okay, because I am going to consider it as a what type 3 region, right? Type 3 region. So my y is going to lie between your 0 and 2 minus j will be better. Okay, fine. Y equal to 2 minus j, right? Okay. So now let us consider this. Let us consider its projection is going to be over this plane. Projection is going to be over this plane. Okay. So over this plane, you see that x obviously is lying between -1 to 1, right? And j lies between what? J lies between 0 and this one. Isn't it? Is it okay?
Yeah.
Just sorry.
Yeah, it is okay now.
Yeah. Fine. So that is why now if I see now the function looks very complicated. The function f, but in fact because I'm only interested in this divergence of this. Here, I think they are going to give you okay. So obviously, I'm happy that this is going to be 0. This is going to be what? Y. This is going to be 2y. Right? So divergence is this. So now, if I have to find out the flux, right? They say that yes, I have to find out the flux.
Yeah.
So if I use divergence theorem, so
3y
dv, okay. So now I can definitely write it down. J going from
0
no, firstly y, right, sorry. Y going from 0 to
minus z.
Then 3y dz dy dx and no dy dz, sorry, dy dz dx, okay.
Yes.
So j goes from 0 to 1 minus x squared.
And
This goes from 1 to plus 1 to minus 1 to plus 1. So obviously you can easily work it out, and the answer is your 184 by 35. Okay, 184 by 35. Okay, so I guess that brings an end to this course. So I guess I have been able to finish the whole syllabus, and again with the help of the problems that we are going to consider in the tutorial sheet, I guess the concepts are going to be more clear, and eventually you'll be able to see this multivariable calculus course. This is very important for the to-be engineers, because all this stuff, particularly the last part, your Green's theorem, Stokes theorem, and Gauss Divergence theorem. So all of these you are going to use quite frequently in your application part. It has got a lot of engineering application. Okay, so I really enjoyed time teaching you. I hope you guys enjoyed it too. So maybe,
yes, enjoyed it.
thank you. So maybe with that note, we are going to end this course, and I'm going to see you in the different exams.
Yeah, thank you.